briefing for your upcoming promo examination. Okay? Right, so for the papers, there are 2 more papers that you are sitting for your promo exams. There is paper 1, which is multiple choice plus multiple completion question. So multiple choice, you're very familiar with. Multiple completion is those type where they give you option 1, 2, 3. Then there are option A, 1, correct. Option B, 2 and 3, correct. Option C, 1, 2, 3, correct. That's multiple completion. Okay, so there are a total of 30 marks, 1 mark each, 1 hour is given for you to complete. So on average, 2 minutes, 1 question. Paper 2, which is happening on the same day, there are 2 different sections. Section A, which is structured question plus data response question. Okay, 40 marks in total, about 6 to 7 questions in total. Okay, alright, section B, free response, 2 long questions. Each question is 20 marks. Okay, all are compulsory. Okay, so there's no choice of the questions that you can choose. Okay, and I will just want to highlight to everybody here, okay, do not antagonize your examiners. Please begin each section B question on a fresh sheet of paper. Sheet means a new piece of paper. Okay? Alright, and there will be 40 marks in total for section B, that's 2020. So in total, paper 2 is worth 80 marks. Okay? Right, and then paper 4, which is your practical, has already been taken already. Right? So what's going to happen next year when you sit for your A-levels is paper 2 and paper 3 will be split out from structured and free response questions. So this will be paper 2, this will be paper 3. Right, next year. Okay, that's why there's no paper 3 this year. Okay? So the scope of topics, if your tutors have not gone through with your, okay, now I've listed out all the topics in H2 chemistry. Okay? Now we are already more than at the halfway mark. We've gone past the halfway mark of the syllabus. We are now lecturing on alkenes, and we will finish alkenes by the end of the week. You will be tested for promos for the topics in red. So all the way from atomostoichiometry up to introduction to organic chemistry. Okay? Alright, but we must begin with the end in mind. We are preparing you all for A-levels, and for A-levels, we still have a bit more to go before we finish the whole syllabus. Okay? So when will we finish the syllabus? By May next year, we will finish the whole H2 chemistry syllabus. Okay? Right? So we will test you all the way until introduction to organic chemistry. Right? And we are here. Okay? And so keep the aircon a few more minutes to cool you all down. But we will continue with alkenes. Alright, but before that, if there are any questions that you have on the topic, okay, please remember we still have the Slido website up. Okay? Alright, so if you have any questions during the lecture, please feel free to ask. We will answer it within a few days. Okay, so the handle is 2018 Year 5 CAT, Wi-Fi CAT. So last week, now Mr. Asmi started off with an introduction to alkenes, showing you all how to name, what is the type of hybridization across the double bond, which is sp2, what are the different ways in which you can draw isomers, which includes the constitutional plus C strands. Okay, so today we will look at another part of alkenes, which is how do we prepare alkenes. Okay, now we will slowly build up the range of reactions. Okay, alright, so we have already learned alkanes, where we saw that they could undergo free radical substitution. For alkenes, we will learn more reactions, and we will build this up such that you are able to suggest ways to synthesize different chemical organic compounds. Okay, right, so alkenes, how do we get them? Okay, in the industries, we do cracking of crude oil that Mr. Asni mentioned last week. So we take crude oil, we do fractional distillation to the different fractions, especially for the large chained crude oil molecules. We break them up, we crack them to give more useful, smaller fragments that we use. Okay? So organic chemistry for now is very, very dependent on crude oil because that's the source of many, many organic compounds. Okay? Which is why if you read the newspaper recently, you'll find that nowadays, apart from drawing oil from the wells, okay, another way of extracting useful organic materials from the seabed, for example, is this thing called fracking. F-R-A-C-K-I-N-G. Okay? Which does have its own set of environmental impact which is not very good for the environment. Okay? Right? But companies and human beings are so dependent on fossil fuel that they'll do anything and everything to extract as much oil as we can from it. Okay? Right, so during cracking, we will break the larger molecules into smaller alkanes or alkenes or even H2 gas. And this is done with strong heating and with the use of catalysts. So for example, I have a very long chain carbon. This carbon is 12 carbons long under very harsh conditions. Okay, very high temperature, in the presence of catalysts, I can break them down into smaller molecules that are more useful. So for example, an alkane can give me an alkene, which I can use for different reactions. Okay, so how else can we prepare alkenes in the lab? Okay, one way of producing alkenes or double bonds is through alcohols. If I have an alcohol which is an OH group attached to a carbon, okay, an alcohol can be dehydrated. So when I say dehydration, I mean I'm removing water, right? And when I remove water, okay, I'm taking out a very small molecule out from the original molecule. So this process of removing a small molecule from a bigger organic molecule is called an elimination reaction. I eliminate out a water from the alcohol, so this is called an elimination reaction, okay, which we have seen in Introduction to Organic Chemistry. So in alcohol, if I were to add excess concentrated H2SO4, heat, I will be able to get an alkene, okay, plus water. Okay? Alright, so I will need this excess concentrated H2SO4 heat. Okay? Alternatively, I could also heat the alcohol with aluminium oxide. So a common name for aluminium oxide is called alumina. Okay? So why do you need to use this particular reagent? What is excess concentrated H2SO4? Now, if you don't know, concentrated H2SO4, okay, is a compound that loves water. Okay? So it will pull water to itself to help in the elimination reaction. And of course, it will also react with the OH group over here. Okay, that will interact, and that kickstarts the whole reaction to eliminate the water molecule. Okay, so water will then be removed, so this is the elimination reaction. Okay, another possible way for us to get a double bond, okay, is to react a halogen derivative, okay, or this is called alkyl halide. It is basically an alkane, but it has a C halogen bond. So this could be a halogen like BrCl. Okay? So I could also dehydrohalogenate the molecule. D means I remove a hydrogen. I also remove a halogen. So what I do is I will remove a H and I will remove a halogen from the molecule. So once again, this is also a elimination reaction because a HX is removed. Okay? Alright? So when I remove a HX, I basically remove a H from one carbon and the X which is on an adjacent carbon. So this H must be on an adjacent carbon before I remove it. Once this HX is removed, okay, HX is an acidic molecule, right? It will react with the base to give you salt and water. Okay, so that's why even though you eliminate HX, you don't see HX in the product because it has reacted with sodium hydroxide and potassium hydroxide. So for the reagents required to do this, you will need a base that is dissolved in an organic solution. Okay, sorry, in an organic compound like ethanol. Okay, so usually we will say alcoholic KOH or ethanolic KOH of NaOH. Okay, right? So you don't use aqueous KOH or aqueous sodium hydroxide. Okay. Not only that, do we need this set of reagent, we also need a condition called heating under reflux. Okay? So this set of conditions is not something that we have seen. So what is heating under reflux? We'll look at that a bit later on. Okay? So one example of elimination reaction involving an alkyl halide is bromocyclohexane. When I heat under reflux this molecule with ethanolic KOH, okay, I will eliminate a Br and a H on an adjacent carbon which is here. Okay, so that's how I end up with a double bond. The HBr that is formed will react with KOH to give me the salt and water. Okay, so the process of heating under reflux is shown here. This is the heating under reflux setup. Do you need to know this setup? Yes. Okay, you need to know how to carry out this heating under reflux reaction. And we will get to do this next year when we do practical. Okay, but if you think about it, what's the difference between heating and heating under reflux? Okay, now the key difference between heating and heating under reflux is when you heat something under reflux, typically you want to react it over a very long duration. For organic molecules, we usually need to heat it for very, very long periods of time. Why? Because in organic reactions, we need to break bonds. We need to break very strong covalent bonds. That's why we will need to heat the organic molecules for very, very long periods of time. For example, 24 hours, 48 hours, 72 hours. So to heat an organic compound for a very, very long duration, okay, it will very easily dry out, right? Because the solvent gets lost as I heat it. Okay, but if I don't want the solvent to get lost in the process of heating it for 2 days and 2 nights, I need to make sure that there's some way for me to recycle the solvent. And that's when this setup comes into play. I have a solution of organic reaction that I want to carry out. Okay. Alright, this is called a round bottom flask. It's round so that there's even heating throughout. Okay. I have inside the reaction mixture, I have boiling tubes to help make sure that the boiling or reaction takes place and doesn't all boil off at the same time. Okay. I connect the round bottom flask to a Liebig condenser. So what the Liebig condenser does is, it has an inflow of water in and an inflow and an outflow of water from the top. So what happens is, this region is always kept cold or cool by the water that's constantly flowing in. And as a result, this part is always cool. So when the reaction mixture is boiling, the gases or the fumes that comes about from the boiling or boiling process will be able to condense on this part of the condenser. And as it condenses, it will drip back into the reaction mixture. So in this process, you find that it is much more difficult to heat this to dryness, almost impossible. So even though there is an open top at the top end of the Liebig condenser, this reaction will not be heated to dryness because the solvent is constantly being recycled back. So that's why it is a reflux reaction. Okay? Right? And so some of you all may ask, why must my water come in here? Okay? Right? Why must the water come in here? There are two possible reasons I can think of. The first reason, okay, is because if I want this region to be the coolest part of the whole experiment, my cold water should be introduced at this point. Because if I introduce cold water here, I may have significant loss of the solvent from the top. That's one way of thinking about it. I start the cooling as soon as I can. Okay? The other reason is a practical reason. Okay? If I add water in from the bottom, it will fill up to the top before coming up. Right? So the whole Liebig condenser will be filled with water in the whole column. But if I add water in from the top, okay, it will not fill the whole condenser. It will just flow down and flow up. So it will not surround the whole condenser. So you will not get efficient cooling. Okay, so that's the other reason why you want water in here, water out from the top. Okay? Alright, so when you do elimination reaction, you will end up with alkenes. Okay? Sometimes there's more than one possible alkene that can be formed. So if there's more than one type of alkene that can be formed, how do we know which one will be formed in greater quantities? Okay? That's when the SAYTZEFF's rule comes into play. Okay? SAYTZEFF's rule tells us something. They tell us that if there is more than one possible alkene that can be formed from a reaction, an elimination reaction, okay, the more stable alkene will be the major product. So that sort of makes sense. The more stable it is, the more that it will be formed. Okay? Alright? But what is a more stable alkene? A more stable alkene is the alkene that has the most number of substituent groups. Okay? And what do I mean by substituent groups? It means things like alkyl groups. The more alkyl groups I have on the two carbons with the double bond, the more stable it will be. Okay? So sometimes we call these alkyl groups R groups. So it means the more R groups or alkyl groups I have on the carbons on the double bond, the more stable it will be. Okay? The reason is due to hyperconjugation, but it's not in the syllabus. So if you're interested, you can go and read up on what is hyperconjugation. Okay? So let me give you an example of how we can apply SAYTZEFF's rule. Just look at this butane 2-ol. So there are 4 carbons because it's butane means there is no double bond. Okay? 2-ol means the OH group is on the second carbon. So this is second carbon because I start counting from here. Count 1, 2, 3, 4. Okay? When butane 2-ol undergoes dehydration or elimination reaction, I will remove the OH group and I will remove a H from an adjacent carbon. So where are my adjacent carbon to the OH group? Adjacent carbon is here. Okay? So I can remove this H with this OH. And when I remove these two groups out, I end up with but1e. Alternatively, this carbon has also got another adjacent carbon which is here, on carbon 3. Carbon 3 also has got a hydrogen. So I could remove an OH and this H on carbon 3. And when I remove these two groups, I end up with a double bond between carbon 2 and carbon 3, which is this. Okay? So I have two possibilities. This Bu1 in, this is Bu2 in. Which is more stable? The one that is most substituted. So look at the double bond over here. This double bond, this carbon bonded to H, H. No substituents. This carbon is bonded to a H and an alkyl group, a CH2, CH3. So this alkane has only got one substituent. Okay? Look at the next one, Bu2 in. Double bond is here. This carbon here has got one H and one CH3. Okay? Which I will count as one substituent. So you don't need to care how long or how short is the substituent. If it has a substituent, count it. So I don't need to be bothered that this is a bit shorter than this one over here, which is 2 carbon. This is 1 carbon, it is still one substituent. So this carbon has one substituent, this carbon has got a H, which is not a substituent, and a CH3, which is an R group, an alkyl group. So this is a second substituent. So this alkene has got 2 substituents. 1 substituent, 2 substituent. The one that has 2 substituents must be more stable. So that's why after I react butane 2-ol with concentrated H2SO4 in excess that I heat, I will find that I will get more Bu2 in. Why? Because Bu2 in is more stable. So 80% of the product will be Bu2 in and only 20% will be Bu1 in. Okay? So that's what SAYTZEFF's rule help us to predict. We know which is the more stable product. Okay? Alright, so like what I said, to get Bu1 in, you eliminate this two. To get Bu2 in, you eliminate this two. Right? Can we have a go at your exercise 2A? Right, try it out. Get an idea of where can you find the adjacent hydrogens or the groups that will be eliminated. Okay, then identify or predict what should be the major product. So there will be more than one product formed. That's great. And once you're done, you can move on to 2B. saw lots of y'all getting to one answer, and then you tell me that that must be the major product. Okay? Right, but to solve this question, you cannot just give me the first product that you see and tell me that that's the answer. Okay? Now, this is what many of y'all saw. To have an elimination reaction, I will eliminate a Br with a H on an adjacent carbon. This Br is on this carbon. Is there a H on an adjacent carbon? The one that you see most often is this one here. Okay? So you could eliminate this Br with this H. You will end up with this. Okay? And that's how you luckily got to the answer. But you cannot evaluate that this is the major product without seeing what are the other possibilities. Where else can I have another elimination reaction? Where can I find another hydrogen on an adjacent carbon? This Br is on this carbon. Are there any other hydrogens on adjacent carbons? Yes. The one on the right, these are adjacent carbons. These are also adjacent carbon, hydrogens on adjacent carbons, alright? So I can eliminate the Br with these H's or these H's, one of them. And when I do that elimination, I will end up with this. You must identify both first, then evaluate which one is major. If I have an elimination with the red rectangle here, I will end up with a double bond between these two carbons. And when I end up with a double bond between these two carbons, I have this structure. How many substituents are on this alkene? This is not a substituent. This is not a substituent. On the other carbon, one substituent. Two substituent. So this has two substituents. The other product, the one that most of you drew straight away, one substituent, 2, 3, 4. Four substituent. 2 versus 4, 4 has got more substituent, is more substituted, then it must be the major product. Okay? And that's how you get to the answer. Okay? Alright, another thing that I observed as I was walking around, some of y'all wrote me the complete balance equation. Right? But if you read the question, did they ask for a complete balance equation? They didn't. So you don't need to give me a complete balance equation unless I tell you to. So for organic chemistry, you don't need to write balance equations unless you really want to. Okay, but there's no such need. Okay, so just give me the structure of the major product. Okay. Alright, next, if you look at 2b, predict the major product of the following reaction. I hope you can see that for this elimination reaction, there are also two possible elimination products. Okay? You can get this when you eliminate an OH with a hydrogen on this carbon with the methyl group. Or you can eliminate this OH with a hydrogen here. Okay? Then you will end up with this product. So once again, you go and count the number of substituents. When I have a double bond here, like this, how many substituents do I have? It is a ring, but you just count it. This carbon has got one substituent. This is a H, so no count. This carbon has got how many substituents? This carbon has got one substituent also. So this product, this possible product has got two substituents. This product, how many substituents does it have? 3. 1, 2, 3. So there are 3 R groups on the 2 carbons with a double bond. But there's only 2 R groups here. So this must be more stable, hence this must be the major product. Okay? So that's our example 2. Okay? Now the next thing that we will go into is, we'll just look at how to prepare alkenes from alcohols and from alkyl halides. Both undergo elimination reaction. But after you have formed the alkenes, alkenes themselves also have a very, very characteristic reaction. I always want to contrast alkenes with alkanes. What did we learn about alkanes in the previous topic? We said that alkanes are not very reactive. They only undergo combustion, and they also undergo free radical substitution. Free radical substitution, you need UV light or you need a lot of heating. Okay? Alkenes, however, are much more reactive than alkanes. Okay? Why are alkenes much more reactive than alkanes? Just look at the structure. In alkanes, you have sigma bonds throughout the whole molecule. But for alkenes, apart from sigma bonds, you also have a pi bond. A pi bond is weaker than a sigma bond, which means a pi bond is weaker. Because the pi bond is weaker, you will have lots more reaction for alkenes. Alkenes are much more reactive. Okay? Right? So alkenes are more reactive than alkanes due to the high electron density at the CC double bond. When you have the pi bond here, there is a concentration of electrons above and below the CC bond. Because that's where your p orbitals or pi orbitals are lying. So your CC double bond is electron rich. There are pi electrons inside the CC pi bond. Okay? Because it is electron rich, it will attract electrophiles. Electrophiles love electrons. That's why they are called electrophiles. Okay? So the electrophiles will want to be attracted to the electrons on the double bond. So electrophiles like Br+, NO2+, even neutral molecules like HBr and Br2 will also be attracted. Okay? Alright? So in this process of attacking the CC pi bond, okay, it will involve mainly breaking the weaker pi bond on the CC double bond. Okay, because this bond is weaker. Okay? So when you break the CC pi bond, okay, for example, you react it with Y and Z, you'll find that Y and Z will get added onto the carbons that was originally on the double bond. So when you see that the two molecules are combining to form one product, we learned this in introduction to organic chem, we call this an addition reaction. Nothing is lost from the original molecule, you just added two atoms or two groups in, it is an addition reaction. Okay? And when you have an addition reaction, you find that the structure or the shape changes from trigonoplanar to tetrahedral. So likewise, the bond angle also changes from 120 to 109.5. Okay? So for alkenes, generally they will have different types of reaction. The first is combustion, which I've seen before. It also undergoes addition reactions, of which we will learn one more mechanism called electrophilic addition. Okay? Previous topic on alkenes, we have learned free radical substitution mechanism. Now we will learn one more mechanism called electrophilic addition mechanism. Alkenes can also undergo oxidation reactions. So combustion, addition, oxidation. Okay? So for combustion, Your alkenes burn readily in oxygen to form CO2 and water. Okay? So the general reaction is as shown. Forms CO2 and water. Alright? Now I just want to highlight that because your alkenes are unsaturated, okay, it doesn't have sigma bonds all the way, there is a higher carbon content in your alkenes. Right? Because it's a higher carbon content, it is easier for you to get incomplete combustion. Okay? So when you get incomplete combustion, okay, you will find that the alkenes burn with a luminous smoky flame because there's not enough oxygen to completely react with the alkenes to form CO2 and water. Okay? Because there's incomplete combustion, that's why it's luminous, that's why it is smoky. Because of the unreacted carbons that forms either carbon or other uncombusted smaller organic molecules. Okay? But our emphasis today will be on addition reaction. Okay? Now, your alkenes can undergo addition reactions, and the possible reagents include H2 gas, H2O gas, which is steam, HX, where X is a halogen, so it could be HCl, HBr, etc. And molecules of halogen, Cl2, Br2. All of this can be added across a CC double bond. So when it undergoes a addition reaction, you will break the weak pi bond and add different atoms, different groups across the double bond to give you an addition product. So X and Y can be added to the organic molecule. Okay. The first one is a reaction or addition with H2. When you add H2 molecule, this is simply a reduction reaction. Okay? We call this reduction, we also call this hydrogenation. Okay? Alright? So your alkenes are unsaturated. Okay? If you react it with H2 gas in the presence of nickel, which acts as a catalyst, with heating, you will end up with an alkane that is saturated. Okay? Alright, so from alkene, you can form an alkane. So this is a reduction, or we also call this a hydrogenation. Okay? Right? Now this reaction may look a little bit unfamiliar to you all. But if you have ever eaten margarine, okay, you are eating a product from this reaction. Okay? Now how do we form margarine from oil? If you look at the ingredients for margarine, so things like plantain. Okay? What other margarines you find in the market? Your spread. Okay? Shh. Can you listen to me or not? Okay. Now you find that a lot of these margarines are also used for making cakes, cookies, etc. Okay. One reason why they are so useful for baking is because of this reaction. When you want to spread margarine, you find that it doesn't melt that easily. That's why margarine is a solid at room temperature. Margarine is actually obtained from vegetable oil. Okay, so if you look at the ingredients for your margarine, it's actually written there, partially hydrogenated vegetable oil. So vegetable oils are alkenes. A lot of them are unsaturated. So what you do is, you make it undergo reduction to hydrogenate or to reduce some of the double bonds in the vegetable oil. And when you reduce some of the double bonds in your vegetable oil, it becomes saturated. And when it becomes saturated, the melting point rises. Because now the molecules pack better. Because it rises, that's why the melting point rises. That's why when you spread it, okay, it is spread as a solid. Why is it partially hydrogenated? Because if you continue to hydrogenate it, the melting point goes higher and higher and higher. It becomes more and more saturated. The reason why you find that margarine tastes good is because the melting point is close to your body temperature. The moment margarine touches your mouth, it melts. So that tricks your brain to thinking that it's good for you. That's why you like to eat chocolate, because cocoa butter melts at body temperature. That's why butter tastes good, because it melts at body temperature. Okay? It tricks your brain into thinking that it's good for you. So if I partially hydrogenate alkene to a melting point that is close to your body temperature, I put it onto the tip of your mouth, it melts, you think that it's quite nice. Okay? Because of that reaction here, that's how you form trans fats. Okay? And a lot of articles are telling us that trans fats are not very good for you. Okay? And a lot of them is formed from this reaction. Okay? Next, I can also add halogen molecules across double bond. So I have a double bond here, I can add a halogen molecule. In the presence of CCl4, which is an organic solvent, I will end up with a molecule which is an addition product. So I want you to look at the conditions here. In free radical substitution, I need UV light, I need strong heating. But when I want to react an alkene with a halogen molecule, I just need room temperature. Why? Because now I have a weaker pi bond and I now have an electron-rich pi region here that will naturally attract itself to the halogen molecule. So it will react very, very quickly. So that's why alkenes are so much more reactive. So if I were to add Br2 molecule that's dissolved in an organic solvent, CCl4, at room temperature, I can form the addition product where I have a Br being added across a double bond. Then I end up with no double bond anymore. Okay? Alright? So in this reaction, I add Br2, I end up with the addition product. What would I observe? We will be doing these practicals next year. But what would I see? Now your Br2 is a halogen molecule, so it has a certain color. Okay? It appears reddish brown. Okay? It could appear orange depending on the solvent. You will find that the Br2, which is originally reddish brown, will get decolorized. So when I say it gets decolorized, means it loses its color. So it decolorizes to form a colorless product. Because Br2 is being reacted away, you will find that the reddish brown color disappears. So this is the physical observation for the reaction. Okay? And we will use this as a possible distinguishing test. So if I want to find out whether do I have a double bond in an organic molecule which I do not know the identity, if it decolorizes Br2, I can suspect that there is a double bond present. Okay? So that is a very, very interesting bit for organic chemistry. You now start to be able to make deductions like an investigator. What are some of the possible structures within an organic molecule based on the observations of the reactions that you carry out? And we will be doing a lot of this for organic chem. Okay? Now, I'd just like to spend the last 5 minutes going through the mechanism of this reaction. Now, this is a mechanism that you need to know for this topic, electrophilic addition reaction. Okay? Alright? Now for this reaction, okay, your CC double bond has got the pi electrons that will be attracted to the electrophiles. But it's not as simple as that. Think of it this way. I have an electron-rich CC double bond. My Br2, based on what we learned in chem bonding, is non-polar, right? So why would it get a delta plus, delta minus? It doesn't at the start. What happens is your Br2, when it approaches the double bond, when it moves close to the electron-rich region of the double bond, there will be some polarization. Because there are electrons here, the electrons on Br2 will now get pushed to your right because they want to avoid electron-electron repulsion. So the electrons in the bonds will now move towards the further atom, the Br that's further away. As it moves to the right, the electrons, this Br acquires a delta negative partial charge. This Br acquires a delta positive partial charge. Now it is polarized, and that's when it starts to react. Because this Br is now delta positive, it gets even more attracted to the double bond. So the pi bond will break, which is shown by the full arrow here. When I draw the full arrow, it means that I'm breaking a bond, which is a pi bond, and I'm using the 2 electrons from breaking the bond to pass it over to the Br. So this arrow shows the direction of electron flow. So flow from the pi bond that's broken, flow over to the Br. So this Br accepts the 2 electrons that's coming over. As it accepts the 2 electrons, okay, Br knows that it cannot 一脚踏两船. So if it accepts 2 electrons, it must give out 2 electrons over to the delta negative Br. Okay? So there is no net change in number of electrons. So you will form, this is what we call a carbochem ion with Br minus. So Br minus, okay, will then be formed as it accepts the 2 electrons from breaking the bond. Br minus now has a lone pair of electrons that can be pushed over to form a new bond with the positively charged carbon. Right? So as the 2 electrons are being pushed over, okay, a bond is formed between this C and Br. But this carbon will be positive in charge because it has just lost an electron from pushing the electrons over to this Br. This carbon is then positive in charge. It accepts a lone pair of electrons to react to give the addition product. So in gist, this is what the electrophilic addition reaction is like. So on Wednesday, we will look at this reaction and we'll see, have a bit of practice for electrophilic addition. Okay, so we end here for today. I'll see you on Wednesday. Thank you.